Ladies and gentlemen, boys and girls, welcome back to another video. Here we got our problem session. We got 4 problems. I'm not going to do this one here because it's more of the same old, same old. It'll just be left as a example. But we're going to do one, and we've got. Let's look at the first one. When we find dy dx, and we have this kind of issue with y here, it's not just y equals. We figure we're probably going to be doing implicit differentiation, especially because when you're looking at it here, we can't really solve for y. You know, if it was y cubed, then maybe we could say y equals, 2x squared plus 8 over 3 1/3 this. But because it's squared, really this would be a 2, and then we get plus or minus, we've got issues. So instead, what we're going to do, let me go back here. Instead, what we're going to do is just do our implicit differentiation, and even if you could solve for y, it still wouldn't be easier. What's easiest here is just taking dy dx of everything. So we say that dy dx of this guy plus dy dx of this guy is dy dx of this guy. So let me go ahead and make this red. What's the derivative of 2x squared? This is going to be 4x. Make this green here. Plus, what's the derivative of 3y squared? Well, it's going to be 6y, right? Times dy dx, because you do your chain rule, right? So the derivative of 6y is, or 3y squared is 6y, and then you multiply by the derivative of the inside. And the inside here is indeed dy dx. And then this guy, of course, is going to equal 0 because this 8 derivative is just 0. So this means that dy dx is just going to be negative 4x over 6y, right? Cool. Oh, my cat is up. My apologies. My cat was thing. All right. Number 2, we got a of x equals the inverse tangent or arctangent of 2x squared plus 1. Okay. So we remember, right, arctangent prime, right? This guy here is going to be 1 over 1 plus x squared, right? So we just use that here. So using this, we're going to find that a prime of x, remember a of x is just this guy here. It's going to be 1 over 1 plus 2x squared plus 1, right? But then we have chain rule. So what's the derivative of the inside? It's just going to be 4x, right? And this would be our answer here. This one I will leave as an exercise, but it's going to be the same exact kind of chain rule dealio. Okay. Compute the derivative of y equals 2x to the root x. How do we do this? Well, we just say, it's going to be root x, 2x to the root x minus 1, times the derivative inside is 2. Wrong. This is wrong. This is super wrong, right? You can't just do the power rule if the power is not constant. We can't say e to the x derivative is x e to the x minus 1. Like, surely this is false, right? What we have to do instead is we have to do, if you ever see the x in the exponent, we need to do our logarithm substitution, right? So what we do here is we say that we take an ln of both sides. So we're going to say that ln y equals ln of 2x to the root x, right? And now you can go ahead and pull down your power. And so, you remember logarithm rules, we pull this guy out front. For logarithms, right, it's really important to remember the rule of, that's the whole reason we use them, right? So if you don't remember all the rules of, okay, when you add them, it's really multiplying and stuff like this, it's not the end of the world, but definitely you need to know this one here. You need to know this guy, that ln, you drop the power, it's going to make, it's going to, when you take ln of something with an exponent, you drop the power. So now we have ln y is going to equal root x ln of 2x, right? And now we take our derivatives and we're fine. So we say that taking our derivatives, on the left-hand side, we have to do implicit differentiation. So we're going to say, what's the derivative of ln? Well, it's just going to be 1 over y times what? We've got y prime, because that's on the inside. And this guy, now we do our product rule. Okay, so what is root x? We're going to have x to the 1/2. So this guy times the derivative of this. Okay, really, maybe we would take a little bit more time if this were on a test, but I'm just going to kind of go through it. You can check it if you want. So we're going to have root x. We're going to have root x times the derivative of ln 2x, which is going to be 2. Here we would have ln 2x, right? This guy is going to go to 1 over 2x times the derivative of the inside, which is 2, which is just 1 over x, right? Is that right? That seems wrong. Derivative of ln 2x is going to be 2x. I don't know. Yeah, seems right. 1 over x plus, and maybe there's a slight. Sorry, I'm really tired. Maybe there's a slight issue, but this, at least the algebra. If that's not correct, I mean, this feels right. You know, I don't know. Yeah. No. I think this. Yeah. This should be right. Okay. So root x times 1 over x plus we've got derivative of root x, which is x to the 1/2. We're gonna have 1 over 2 root x times the other guy ln of 2x, right? This here is our answer. And then finally, to solve for y prime, now we say that y prime is y times this whole quantity here. Right? But what is y? This is our final step. Y is this guy. 2x root x. So once we do that, then we're done. So y prime equals 2x to the root x times our above quantity. And that would be your final answer. Okie dokie. That is tweaking. All right, let's get on to our final little bit here, and then we will be done. Okay, so softball diamond has the shape of a square with 60 feet long sides. Whenever you're doing any physics problems like this or any word problems, always draw a picture. You sit there and think, John, I don't need to draw a picture. It's not, I can visualize. Well, you're just making it harder for yourself. Who have you helped, really? Like, now you can say that you don't draw pictures on word problems. Nobody cares, not a soul. But it is super helpful. I always draw pictures for these so I can get all my bearings. I'm not trying to, imagine which way is this way and things like this. And then you're in physics, same thing. Like, just definitely draw a picture. Okay, so all of these are 60 feet. Okay. If a player is running from second to third base, so maybe I'll draw it like kind of like a. I guess I should have just drawn the rhombus as normal. Rotate 90 degrees. No, I needed to rotate like 45 degrees. How do you do this? Whatever, man. Okay, fine. I'll redraw it. Okay, so these are all 60 feet. If a player is running from second to third base at a speed of 25 feet per second, at what rate is her distance from home plate changing when she is 15 feet from third base? Okay. So this is 15 feet. And we're looking at this distance to home plate we will call H, and we want, what is it? What do we want? h prime, right? Our distance, our derivative, you know what I mean? What distance from home plate changing. Perfect. So let's find this. Okay, so all these related rates problems, all they're going to boil down to, step one is draw your picture. Always draw your picture. Step two is going to be write a formula. Step three is going to be implicit differentiation. Step four is going to be plug in and solve. Right? So what we find here is that we've got our picture. So step two, we're going to write our formula. What formula is going to play nicely with h, this guy that we're trying to solve for here, right? Well, clearly the Pythagorean theorem, right? So what we can say is distance to home and distance to third. So maybe I'll call this d sub h and this quantity here. And so maybe you shouldn't have drawn this 15. This was a poor choice. You can always change your pictures as you go. D sub 3, right? Okay. So we have a Pythagorean theorem. Here we're going to say that 60 squared plus D3 squared equals DH squared, right? Because we've got this right angle here. Okay. And maybe I should be careful about these should be subscripts, like for sure ski. I don't know why I didn't draw it that way. Okay, so we've got this formula here. Is there anything else we can do in the terms of formula? Not really. This is kind of all that we're left with. We're not going to do like any sines or cosines or anything. This is what we have. We've written our formula. Now we do implicit differentiations. Let's take our derivatives here. Derivative of the left-hand side is give me a second, please. Yeah, okay. So maybe we could have done more generally, just triangles here. No, but it's fine. So we're going to have here, this derivative is going to be 0. So let's take derivative. We're going to call this guy 3. 3 will be green. Take our derivatives, so 0 plus 2d3, so distance to third base. Maybe I could have called it t for third, but it doesn't matter. 2d3, right? We take our derivative, times d3 prime equals 2dh times dh prime, right? And dh prime is what we're solving for. And this is dh. Sorry for the notation. Okay, so what do we do here? Well, now we can just plug things in. We plug them in here. So what do we know? We know that D3, so 2 times, this guy is going to be 4. We know that D3, we are how far away? We're 15 feet from third base. So this is going to be 15. We know D3 prime is what? 25. We're at a constant 25. Okay, what about the right-hand side? We've got 2. What about DH? How far are we from home? And we'll leave this as DH, and then DH prime is what we're solving for, right? So now we just have to find out how far are we from home, but we can do Pythagorean theorem for that, right? So this guy here, our final little step here, we notice that distance from third squared plus the 60 squared equals our distance from home squared. But we notice that D3 is at 15 right now. So this means that 15 squared plus 60 squared equals DH squared. So then finally, DH is going to be, at this moment in time, we are 15 squared plus 60 squared inside the square root, feet from home plate, right? So that's what we have to solve for. This is for what this is. Perfect. Now that we've solved it, we just go ahead and pop that guy in here and we're done, right? So we're going to say that now 2 times 15 times 25 divided by 2 root 15 squared plus 60 squared is going to be dh prime. Okay, so let's just recap here. We drew our picture. Our picture was nice. Maybe when you find, I think you can split down related rates into two pieces of information. The first piece of information is things that are universally true. So, for instance, she is always moving at a speed of 25 feet per second. The squares are always 60 feet long. And the Pythagorean theorem is always true, right? So this Pythagorean theorem we have is always the case. These are your universal truths, and I would write all of your universal truths in your picture. However, if it says something like, what rate is her distance from home plate changing when she is 15 feet from third base, right? This is not universally true. This is only at one moment in time, right? Because the assumption is that she's starting here and she's running constantly. And at some point, right, so this distance is changing. This is my DH, and now this is my DH, and now this is my DH. And you see how DH is changing. What we're saying is that at all times, in every point of time as she's running, she's always running at 25 feet per second. These lengths are always 60, and the Pythagorean theorem is always true, right? So those would be our universal truths that we draw in the picture. I would recommend against, just for like simplicity's sake and kind of your your mental sake, I would recommend against writing out, how you would write D3 here instead of writing 15. I wrote 15 initially, and you saw the issue that came from that. So, we're just freezing at this point in time. How fast? What's the, how quickly is this distance changing, right? Okay, and then after that, you do your implicit differentiation. You get this guy here. Maybe, like in our example, you've got one more little guy to solve for. And that's once again going to be taking into account the specifics of the problem, like of, at this, when she is 15 feet away, or when the boat is 10 feet away, or something like this. You know what I mean? That's kind of when you sometimes solve here. And then you just do your algebra and you're done, right? Okay, wonderful. So if you have any questions, feel free to email me. I hope that you all have a wonderful weekend, and I will see you on the morrow. We've got, today was supposed to be a review day. Whoopsie. We don't have, okay, maybe I can, maybe I'll probably make a video maybe on Monday, and I'll post the video on Monday. It'll be a review, like I'll be doing over the practice exam like I did the last time, and I'll make the practice exam public now so that y'all can kind of take that whenever. But email if you have any questions. I'll see you on the later, and peace.